Okay, I'm getting a message here from the organizer, so we should probably get going on time. So welcome back, everybody. It was a really great start in the morning, and I'm chairing session 2. So we have 3 talks. Again, this session, I'm going to get out of your way, but just quickly mention, we'll use the same format, 20 minutes of talk, then 12 minutes for discussion, and 3 minutes, if possible, for questions. If there are questions, please do use the chat, and I'll be monitoring the chat. So our first presenter is Jiasun Lee from George Mason University. So whenever you're ready, the floor is yours.
Okay. All right. You can hear me, right?
Yeah.
Great. Okay. Thank you, Evgeny, and thank you for the organizing committee for putting the paper on the program. So this work is joint with Hana Haraberta and Jiguohe. And this study is motivated by the observation that in recent years, a lot of new blockchain applications are built on the so-called Byzantine fault tolerance protocol, right? So this underlying the Bitcoin so-called BFT protocols is a classic problem, so-called Byzantine generals problem. It is a very classic problem in computer science. It actually dates back to the 1980s. But because of the rise of blockchain, there's a resurgence of interest into these protocols. And a very important distinction between what people talk about BFT now and what BFT has been studied in the 1980s is that the Byzantine fault tolerance protocols, when they were first developed, they were developed to applications for distributed systems within a single entity. For example, a large tech company may have multiple computers. So they are these protocols work in a trusted environment. And the so-called Byzantine behaviors really capture that sometimes some computers may experience some technical glitch. But when we try to, and also some of these projects mentioned here, when they try to apply the BFT protocols to blockchains, we're effectively changing a trusted environment to an adversarial environment, because the participants in those applications may have their economic incentives. Okay. So taking the perspective from an economist, right? Those classic Byzantine fault tolerance protocols, they have the following 3 assumptions. First, there are some so-called Byzantine nodes that they may, for example, experience technical glitches, that they just may behave arbitrarily, that do not follow what the protocol prescribed them to do, which I will explain, like what do we exactly mean and how those BFT protocols exactly work in more detail later. Okay? And they assume that for all those nodes who are not Byzantine, then they are so-called honest. So they will just faithfully follow whatever the protocol tells them to do. And finally, just by the nature of being a distributed system, whenever nodes make decisions, they have to follow their local information from peer-to-peer communications. So no single entity within the blockchain system will have a global view of what is going on. Okay? So this might all seem a bit abstract to you right now, but then it will be make more substantiated when we introduce our model. Okay? So the biggest the biggest contribution that we would like to do in this paper is to change this honest assumption within the BFT protocols. So instead of assuming that the nodes are honest, we assume that those non-Byzantine nodes are rational. Okay? And then we still retain the feature that Byzantine nodes may behave arbitrarily. So for rational nodes facing nodes who are crazy and may not just may behave arbitrarily, the way we model that is to borrow from the economics insight of ambiguity aversion. Okay, so those rational nodes, they have their well-defined incentives, which I'll explain later, and they are ambiguity averse about what non-Byzantine nodes will do. And we'll look at what would be the equilibrium coming out of these BFT protocols and shed some light on how we should design and how design these protocols and how these protocols will behave. Okay. So let me jump into a simple model. That is the model the basic baseline model that we'll analyze in our paper. Okay. So we call this is a consensus game. So there is a continuum of computer nodes and with measure n, okay? And the game will proceed in the following steps. First, nature will randomly select one node as a leader. And then we call all other nodes that is not the leader as backups. Second, the leader will decide whether to send a message to all the other backups. Okay? So for example, in the application of blockchain, this message may just contain a batch of new transactions that has just occurred. Okay? And then after that, each backup may decide on whether to forward the message received from the leader to other backups. So we call this a peer communication. Okay? So, so if they receive the message, then they can take the peer communication can take place. So once this messaging stage and the peer communication stage are done, based on their local information, each computer node may decide on whether to commit to the message that has been communicated. Right? Suppose in our case here, everybody commits to their message. Okay? So a committed message can just be think about as like a set of information that has achieved consensus. Okay? So this is really just a very simple model that we are going to analyze in this paper. So this is a backbone of what almost all BFT protocols work. So if you are more into the computer science literature, then you'll see that like the BFT protocols that has been used in practice are effectively just adding more bells and whistles to our baseline model, but it captures the essence of all these different variations. So if all nodes just simply follow what we have just been prescribed here, then this analysis is going to be very simple. Okay. The challenge with the Byzantine fault tolerance protocols is that some of these nodes may be Byzantine, so they may take arbitrary actions. Okay. So we, in our paper, we assume that out of the n measure of nodes, f of them are Byzantine faulty. Okay. So for example, some nodes may be Byzantine faulty and may not necessarily follow what the protocol tells them to do. But the problem is, of course, is that we do not know who is Byzantine faulty, right? We know that some of the nodes may be Byzantine, but we don't know whom they are. If we know this for sure, right, then for example, if we know this node is Byzantine, then we can just exclude in this consensus process, then everything will be very simple, right? So traditional BFT protocols tries to achieve the fact that even though we don't know who is Byzantine, but as long as we know that a fraction of them are Byzantine, then we may still obtain good consensus outcomes. Okay? So in our model, so all these nodes that are not Byzantine will be called rational nodes. Okay? So by saying rational nodes, then we need to give them well-specified utilities. Okay? And we specify the utilities as the following, and we'll see that how it corresponds to what traditional BFT protocols work. Okay, so so first of all, in the game, right? So first of all, there's this sending stage, and then there's peer communication stage, and then based on their local information, each computer nodes decide whether to commit to their message. So by the end, they have a decision on whether to commit to the message or not to commit to the message. Right? If they commit to the message, if they do not commit to the message, they will get a payoff of 0. If they commit to the message, their payoff depends on whether the message that they commit to actually achieve consensus. If they commit to a message that achieves consensus, then they'll get a reward. If they commit to a message that does not achieve consensus, right, they will be penalized. Right? So there's a reward C and a cost C. Okay? And what do we mean by a message reaching consensus? A message reaching consensus in our model means that the message, so all the rational nodes, or up to, except for a measure 0, right? Basically, you can think about there's a unanimous agreement, a unanimous commitment to this message. If there's unanimous commitment to the message, then consensus is successful, okay? So you can see that this game is a dynamic game because there are multiple stages in it. There's also a game of imperfect information because in this peer communication, I only know what is communicated to me, and I don't necessarily know what others know. I don't have full information about that, even though I can make some inference about it, which is going to be important. And also it has this coordination feature because you would like to commit to something that others also commit to, right? And finally, the game also has a cheap talk kind of nature in it because the final outcome is only dependent on what my commitment decision do. It is not directly affected by the peer communication, even though the communication may have indirect effect on what commitment decisions people take. Okay? So the solution concept of our game is going to be a perfect Bayesian equilibrium with a adaptation so that the rational nodes will have multipliers over Byzantine node strategies. And this is where that rational ambiguity version toward Byzantine strategies are modeled. Okay, so I think our biggest contribution is actually kind of setting up just interpreting these traditional Byzantine fault tolerance protocols within economic framework. Now, given this framework, we also want to show that, well, this framework is actually useful, right? So we would like to draw some implications coming out of this. So the first thing we would like to do is that within this simple model, we can actually characterize all symmetrical equilibria, okay? So what are the possible, could be in a candidate symmetric equilibrium? First, in equilibrium, a rational leader will send messages to each backup with some probability P. And a rational backup will forward messages if received with some probability Q. And finally, a backup will commit if receiving certain number of messages with one from the leader, or commit to the message if receiving some other set of messages and none of which is from the leader. So all the P, the Q, and the set here are what we need to determine in equilibrium. But any set candidate equilibrium will satisfy, will have this structure. Okay, so we'll start from this structure and first characterize some of the necessary conditions for it to be an equilibrium, and then we pin down some of the conditions for equilibrium to exist. Okay. So so before we proceed, right, it's something that worth pointing out is that if there's always going to be a so-called non-consensus equilibrium in which like just nodes just discard what is being communicated and just never commits to their message, right? So you can think about it's kind of similar to like Babel equilibrium in cheap talk games. But we are also interested in consensus equilibrium. So that the nodes, the leader will send messages with a positive probability, and the backups will forward messages with a positive probability. Okay, let's proceed. So let's first give some preliminaries in characterizing the equilibrium. So first of all, here we have a horizontal line that indicates how many messages that a node can achieve. Right? The maximum number of nodes that messages a node can achieve in any equilibrium, in a candidate equilibrium, is going to be n minus f multiplied by q plus f. Why? Because if the leader sends message to everyone, and n minus f of them will be going to rational nodes, who will forward them with probability q. And then the Byzantine nodes may forward all messages, right? So the maximum number of messages you can receive is going to be this number. Second, we also see there's an interval that is consistent with the leader being rational, right? If the leader is rational, then in our candidate equilibrium, the leader will send messages with probability P. And then n minus f multiplied by P, rational nodes will receive the messages and they will communicate, they will forward it with probability Q, okay? And then plus f, then this is the lower bound. Then the upper bound is this number plus fp, right? Because fp number of Byzantine nodes may receive the message, and they may just forward it all together, right? So that's why, so you may receive messages within this region. So if you ever receive messages outside of this region, then you can make inference that the leader is Byzantine. If you receive messages within this region, then you don't exactly know whether the leader is Byzantine or not, because of course, this region is consistent with the leader being Byzantine, but being rational, but the Byzantine leader may also mimic the behavior of a rational leader, right? So you cannot really tell, but you can really tell when you are outside of this region, okay? So second, we would like to see that given the number of messages you receive, we can also make inference about how many messages other nodes receive. So this is very simple, is that for any messages I receive, I can always infer that the other nodes receive a number of messages is going to be within the band of a length 2f, right? This is because if I receive a certain number of messages, there's one extreme is that all the Byzantine nodes send messages to me and do not send messages to others. So then others will receive f fewer messages than I do. Or another extreme is like the Byzantine nodes do not forward messages to me at all, but they forward all messages to other rational backups. So then the other rational backups will receive f messages more than I do, okay? And this observation is going to be useful for us to pin down the rest of our results, okay? So then what we are going to show now is that it's something actually very interesting, is that in any candidate equilibrium, nodes will not commit when you are outside of this blue region, but you will always commit when you are within this blue region, okay? And the idea is actually can be very simply derived by iterated deletion of dominated strategies. So here's the very simple idea coming out of this. Suppose that I do not receive a lot of messages, right? I receive messages fewer than f, okay? And then I know that based on what we have shown earlier, right? Others may receive f messages fewer than I do. So other rational backups may not receive any messages at all. If they do not receive any messages, they will not be able to commit, right? So if they do not commit, then consensus will fail. And because I'm ambiguity averse, I think about the worst case outcome. I know that they will not commit. So I think that if I commit, the worst case outcome coming to me is I'm going to be penalized because I commit to a message that does not eventually reach consensus, right? So what does that mean? That means that, well, I will not commit whenever I receive fewer than f messages. So then we can just push this reasoning forward, right? If I receive fewer than 2f messages, then I also know that others will receive fewer than f. It may be possible for others to receive fewer than f messages. And because I think about the worst case outcome, that means I will not commit if I receive 2f messages, right? And you can see this logic can just be repeatedly pushed forward until some point here, okay? And this point is like, we put this lower bound here and plus f here, okay? And then if we get more messages, then I also know that it's possible that other nodes receive messages within this small interval here. So that indicates that I should not commit either, right? So that simply indicates that we should never commit whenever I receive messages outside of this blue band. Okay. Of course, there remains a question of whether I should commit or not if I'm within this blue band. Okay? And the reason we are going to show that unless it's a non-consensus equilibrium. If it is a consensus equilibrium, we will always commit whenever you receive messages within this blue band. Why? We can actually show with a contradiction, is that suppose that, well, because if we are in a consensus equilibrium, that means that I need to commit at a certain point, maybe like at this green point here. It also means that, okay, if by contradiction there exists some red point in which nodes will not commit, then it will lead to a contradiction, because when I receive these number of messages, I know that it's possible for others to receive messages like within this blue point here. And if they do not commit, then it will be silly for me to commit, because I will be committing to a wrong value that has not reached consensus, right? And by contradiction, that means that I will always commit in this blue region, of course, right? So,
Jiasun, sorry to interrupt. It's time to wrap up if you can.
Okay, yes. All right. So basically, this is the basic structure. And then in the rest of the paper, we characterize the conditions for the reward and the penalty so that they indeed commit to their messages. Just indeed, such a strategy profile is in equilibrium. Okay. So basically, we will have a non-consensus equilibrium in a fraction of equilibrium, in an equilibrium in which consensus succeeds when the reward is high enough. Okay, so the implication is that there will be multiple equilibrium and consensus protocols, and we can also, and later on, we also include message losses so that we see that when there's message losses, higher welfare can be achieved when there are idiosyncratic message losses, but there will be a hump-shaped relationship when there are systematic message losses. Okay, I'm going to stop here. Thanks.
Great. So there's a question in the chat. We can get to it at the end, but if you can read it and you can answer it by typing, please go ahead. The discussant for the paper is Ye Li from Ohio State University.
Someone need to enable me share the screen.
Okay. Evgeny, if you can look into it, but I'll also try mine.
Maybe that's stop shared.
Yeah, it's all done. It's good now.
Right. So first, I want to thank the organizers for inviting me to discuss this very interesting paper. This paper has always been on top of my reading list, and it's a great pleasure reading this paper because it has a very clear contribution. This paper studies a very general problem that is often studied in the computer science literature rather than the economics literature, which probably suggests it's more important than we thought. So protocols based on decentralized consensus avoid single point of failure. That's why we start to analyze all these decentralized protocols, right? We all know that traditional financial systems, they suffer from this single point of failure problem, whether it's operational risk or it's financial risk, moral hazard, all of this. But if you decentralize it, this can be avoided to some extent. But the concern is that some of the nodes on the decentralized network can be faulty or be hijacked by hackers. This is what we call the Byzantine nodes. There is this famous Byzantine general problem. Basically, if you consider there are, let's say, 7 generals, they need to either coordinate to attack the enemy or retreat. And if half of the generals attack and the rest retreat, then this will be the most disastrous outcome. So they need to arrive at a consensus. But if there are 3 decide to retreat and 3 decide to attack, then the 7th general probably send a message to the people who want to retreat. It's a retreat. And then send a message to the people who want to attack. And then this 7th general is basically in the position to screw up everyone, to screw up the plan, and to impose losses on all the people involved, right? So of course, this 7th general has its own incentives. So that 7th general is what we call the Byzantine node. But here in the computer science literature, we typically think about the behavior of Byzantine node as some random arbitrary behavior that will disrupt the decentralized system. There are 4 features that typically studies on this Byzantine fault tolerant protocols emphasize. The first feature is that the Byzantine node behave arbitrarily, as I said before. The second is that the non-Byzantine nodes, they are quite concerned about the worst case scenario regarding the Byzantine node's actions. And this is why the authors use the ambiguity aversion utility function, which I think is very, very reasonable. And the third feature is that the nodes, they always act upon this local information. They are not able to observe the full topology of messaging. Basically, they do not observe how people send message to other people and what is the nature of the message. And last but not least, very importantly, the existing studies typically model non-Byzantine nodes action as following some prescribed strategies. Or sometimes we call these nodes honest nodes. But we all know people have incentives, right? So this is the key contribution of the paper, that is to model rational non-Byzantine nodes by emphasizing their trade-off in terms of benefits coming from reaching consensus and the costs coming from a consensus failure. They also provide an excellent literature review in the paper that touches upon both studies in the computer science literature and also economics literature. I highly encourage you to read the paper, and particularly the literature review. It's very educating. My comments will be focusing on extensions, will be focusing on applications, because as I read through the model, I think I don't have any problem with the proofs. I don't have any problem with any of the result. I think it's a very watertight execution. And as I laid out here, right, you have 4 features that people typically emphasize, but the last one here is really against our, economists' instinct, right? So we want to model rational agents, and this is exactly what this paper does. So I'm not going to challenge the assumptions, the results. So all that I want to do is to provide some extensions. Maybe the authors can think about these comments as writing the next paper, or maybe add 1 or 2 sections to make this paper even more interesting. So first, the authors consider a particular type of Byzantine strategies. I think that's a very relevant type. And what I want to emphasize is that some of these Byzantine nodes, they also have their own incentives, right? As I mentioned at the very beginning, this original Byzantine general's problem, the 7th general who wants to screw up everyone certainly has his own calculations. So maybe it is worthwhile to think about this game not as Byzantine nodes that behave arbitrarily versus rational non-Byzantine nodes. But we can think about the rational Byzantine nodes who has their own trade-offs, and non-Byzantine nodes, of course, face their own trade-offs. And when it comes to practical applications, of course, hackers have their own trade-off when it comes to hacking the system, right? So, but I don't think the author can really go all the way, lay out the Byzantine players' preferences based on the game outcome. They can certainly do this, but this warrants a new paper. So what I think is that the authors can provide a discussion on, to what extent, right, the Byzantine strategy profiles analyzed in this paper can be potentially rationalized. On what kind of Byzantine players' trade-offs can be the underlying forces that generate this strategy profile. Maybe 1-2 paragraphs discussion will just suffice. So my second comment is on this, how computer scientists, they model the non-Byzantine nodes. They model them as honest players who follow the prescribed strategies. Actually, if you think about it from a practical perspective, this is not a very bad assumption, because there are costs to rationally deciding on things, right? We need to pay attention, and maybe we don't need to pay attention if we are able to write a piece of code that can automatically execute whatever we want to do on a state contingent basis, right? But not every node has this ability. I certainly do not. Jiasun certainly has. So, people are different, and maybe you can consider a fraction of non-Byzantine nodes that are lazy and just follow the prescribed rules. And maybe the protocol can give some reward to this non-Byzantine honest or lazy players to follow the prescribed rule. And in this sense, how should we design this prescribed routes, right, for this fraction of lazy non-Byzantine nodes to follow, especially in the context of the rest of Byzantine nodes being rational, and potentially even the Byzantine players can be rational, right? So this paper characterizes more strategic interactions far beyond what we know from the existing literature. But then if we allow a fraction of non-Byzantine nodes to behave lazily and follow the rules, right? The question is, how do we design these rules to maximize welfare? So I think this might also be an interesting application. My third comment is more complicated to do. I think maybe this is for a follow-up paper. So we can think about an extended game, right? Right now, we focus on 2 outcomes, whether a consensus is reached or a consensus is not reached. But we can also think about the message has a nature of truth or not. So the rational non-Byzantine players and Byzantine players, they can decide whether to send a true message or false message. And if a consensus is reached, whether the message is true, if a consensus is reached, whether the message is false. And if there's no consensus, right? I mean, what is the original message that the leader gets, the true message versus the false message? So we can think about different scenarios. So why do I pay attention to this particular extension? Because in reality, the incentives of these faulty players, they are often, this goes back to my first comment on the incentive of the Byzantine players, the faulty players. So in practice, the incentives of the faulty players, they are often related to the true or false nature of the message. For instance, I'll be a faulty player if I just send 5 Bitcoins to Jiasun and I want to reverse the transaction on the Bitcoin ledger. And I'm going to send a false message. And if the consensus is reached upon this false message, there might be a cost imposed on everybody, except me. And so in this case, we can think about first, the Byzantine players, they have their own incentives. And this incentives is particularly relevant if the message has a truth or false nature. And of course, if we think about this, right, the types of agents can switch over time between a faulty and rational non-faulty behaviors, players. So I think this points towards a more general direction of research. That is, if we think about the design of decentralized system, right, how the consensus is arrived. There are players who have conflicts of interest. We can label them as Byzantine players, non-Byzantine players. We can label them as honest, dishonest. We can label them as players follow prescribed rules and discretionary player who just make rational decisions, right? But what is important is that these players, they have conflict of interest. And under this more general context, how do we design a consensus protocol? But this paper certainly is guiding us towards this direction. So I think it's a very clear contribution. There are new insights and very practical insights. So my comments are in these 3 areas, again, largely about extensions and some discussion, 1 paragraph or 2. But I think the paper is quite complete already at this current stage. Thank you.